So good evening, everyone. I'm Prableen Kukreja, PhD scholar uh, in IIT Tirupati. So this is our lecture 2, as you all know. So any doubts in first lecture? Excuse me, I think. Any doubts in the first lecture? Have you gone through it again?
Yes, ma'am.
So was it fine, or any doubts? Is it?
Just
Is
if
it
you could, the uh, we had a doubt between the I had a doubt between the variance and the bias.
okay? Okay, that we have to cover now. We haven't covered in the last lecture. Okay,
Yes.
one thing we are going slow, but I'm trying to cover all the things. Like I don't want that it should happen I should rush and then I should jump to the lecture week 2. I want that everything should be covered in detail. That's why we are going slow. Is it fine or you want like week by week? So what are your views about this before going to the lecture?
Ma'am, the one that you're going with is fine.
It's good. It's fine. Okay. So it may happen that we might be slow. Like we might not today also catch up all week 2 syllabus. Today also we can't complete. Though some of the things might left, but I want that it should be clear from my end to you. And I was also thinking Slack. Okay, I'll share with you afterwards. Okay, let's start. So last time, just a quick revision what we have done. Last time we have done the supervised learning, unsupervised learning. I hope so that is clear with you, like what is machine learning, what is supervised learning, what is unsupervised learning. That were the basics done. And then we came up with the I have also given you the sheet as well. Maybe I'll share the link on the YouTube comment also. Like someone asked me, I'll share that. Then we also did K nearest neighbor, then somewhat linear regression or k-nearest neighbor, not in detail, but we just touched that part. And then we came to statistical learning, basically. So there was some confusion in the last class. So let's discuss that statistical decision theory. Sorry, not statistical learning, statistical decision theory. Let's start that. So what we had done that, how good or bad the prediction is and how to choose like best function for the prediction. That's what we were thinking, okay, what is statistical decision theory? That what we are saying that what we are predicting, is it good or is it bad? How much good, how much bad? That is what we were studying in the last lecture. And then we actually I derived something that was I think confusing with you. So let's again go through that. So what we did, one more thing, like there is a training data, there is a testing data, there is a prediction function. That things are clear to you. What is training data, what is testing data, what is predictor function, or is there any doubt? Am I speaking very fast?
No.
So are those things clear with you? No, ma'am. So what is the doubt? Okay, the last part where we were doing the stat decision, it wasn't clear. Can you please brief it once? Yes, I have to complete it, and I know that's not clear. So let's try to understand that. Maybe. Let's try to understand that in detail. Statistical decision theory. So as I told you, what is statistical decision theory? I'll just have first brief part and that derivation part. I'll not go in detail. I'll tell you like I'll make it easy. So we learned that, okay, there is X, there is a Y, this is the input and this is the output, basically. And if I talk about the training data, both are given to us. Okay, that's clear. Then there is an fx. What is fx? Anyone?
Output.
Function that generates output.
Yes, yes. So it's a predictor function, I'll say. So our main motive is like to find out the best fx. Why best fx? So that we can generate it the same output, or the output difference should be very small. I mean to say, like, this I have to predict, output I have to predict in the testing data. I have the training data in which both x and y are given to me. Then testing data is like, okay, now we have to test whether our model is, how good our model is performing. Then only x is given to me. And then with the help of this predictor function, I'll predict this y hat. And then we'll see how much difference is between actual y and actual output and the predicted output. Clear? Then we move to the k nearest neighbor and the linear regression. Linear regression, though, I'll have in detail, as there were many doubts in the last lecture also with you guys that, ma'am, why B naught is there? Or I told you what is the role of the coefficient here or weights here. So I'll go in detail with this linear regression. Then we went to nearest neighbor regressor. In nearest neighbor regressor, we said, okay, there are some points x1, x2, x3, x4, x5, x6. Suppose I have to predict the output of this x. So what I'll do, I suppose this is x2, suppose. And what I'll do, I'll see its three nearest neighbors. So 1, 2, 3. And I'll take the average of them. X2, X3, X4, what are their outputs? I'll see Y2, Y3, and Y4. I'll do the average of them. And whatever output will be there, that output is of X. Clear? If you are having any doubt, ask me 100 times. Clear?
Yes.
Okay. Should we proceed? I hope so. This nearest neighbor regressor is clear. Yes, yes.
Yes.
KNN is.
This KNN is clear. Now, then we move to the loss function part, where I think, okay. What is loss function? As you know that, okay, this is the true output, and by fx, we'll have the predicted output. As you told that, okay, it's a function or it's a predicted output, which same thing. So we have to find how much gap is there, how much difference is there. So there is a popular squared error loss function, in which, or I'll say expected prediction error. What it says, expected prediction error. The name itself suggests, okay, we are having the gap between them. What is the gap between them? The true output as well as the predicted output. What is the gap? Square of them and doing the expectation. Y square, so that negative and positive, it shouldn't be like, if it's negative or positive, it shouldn't have a difference. Like if fx is greater than y or y is greater than fx, we only want to see the gap. Okay, I'll tell you, Chavi, once again, what's loss function. Loss function is like, suppose I have predicted 3, but the actual output is 2. So what is the gap between them? That is, sorry, what is the gap between them? There is the 1, 3 minus 2, that is 1. I'm saying in very layman language. So this I predicted, the model predicted. This is the actual output. So gap between them is basically the loss function. Is it clear, Chavi? Now,
Ma'am, would you please do, what is E? Just expected.
okay, this is
E,
expectation.
not EP. E, expectation.
Expectation. So EPE is basically expected prediction error. So expectation of the error, expectation of the predicted error, expectation of error. And as we are taking the squared error means like what is the difference between them and squaring them. So expectation of predicted error. Now, as we saw that, okay, if the function is like how we calculate the expectation. Anyone, can you tell me how we calculate the expectation? I gave you an example as well last time. Like suppose average is expectation. What I'm doing is 1 into 1 by 2. plus 2 into 2, 2 by 2. Basically, I'm summing it up, sum over x into p of x. That is what I'm doing. The probability as well as the sum. This is basically the expectation formula. Now, when I say about the continue, now regression, we know that there are two types of supervised learning. One is regression, one is classification. I'm doing it fast because we have covered in last lecture. Regression is continuous in nature, whereas classification is discrete in nature. Discrete means 1, 2, 3. Continuous means it can go 1.1, 1.1.111 like this. It is continuous in nature. When it's discrete, we usually use sum. And when it's continuous, we usually use integration. Integration in case of the discrete continuous nature. So we can replace this by the integration as well. Like I'll write the easy way. The same thing, summation of x into, p of x, x into p of x. This is the expectation. Now the same expectation I have written like this, only I have replaced this sum with the integration. Rest is same. Is it clear? Yes, Joshan, it's compulsory. And to submit the assignments by deadline. It's mandatory. Okay. Any doubt? Not if you're not getting, ask me. So
Just this part, ma'am, the integration. Integration of y into f of x square means the average of all of them. But then, okay, yes, because it's continuous. Yes, I remember now. Thank you.
okay, many of the students are having doubt. Assignments and all we'll clear at the end of the lecture. Is it fine? Because we are already lagging the syllabus behind. So it's fine. While we'll complete, we'll discuss all the doubts. Okay. So now it's fine, like it's continuous. So instead of sum, we are using the integration, average over. We are just replacing this expectation with this integration. And the formula of the expectation. Now, the main part come in which last time you all were getting confused. So you all are attending both the classes, or only my class, or only her, like how it's happening? So you are attending her other TA's class as well? I just want to know, like both. Okay. What about others? Okay. So what they are covering? They are also covering the mathematical part like this only, the same things. I haven't seen, I don't know about the other TA. Okay. So how this came? Any idea? We discussed any law like last time. How many of you have attended the class last time? I'm sorry, they were waiting.
Law of total probability is what you're trying to.
Yes. I'm sorry, whosoever were waiting in the waiting room. I'm so sorry. I don't know why this it's not getting enabled, like disable the waiting room. Otherwise, there is an option here, but this option is disabled. Like it's not showing me here. Of the waiting room. I want to disable this waiting room, but I'm unable to. I'm so sorry for that, whosoever have joined late. We were just discussing about the last class only.
You can find that option in the host settings.
Yes. More settings. I have gone meeting settings.
No, ma'am, there are host tools also. You can go in there.
Where?
Can
My screen, where?
If you go to more, there is option host tools.
Warning in progress.
Okay. Oh, thank you so much. I've done it multiple times, but I forgot. Thank you so much. Varsha, this is a proper discussion only. We are discussing all the things, and this is the second class. First classes, they're in the YouTube lecture recorded. I'll share it after the video, after the at the end. So, okay, as we discussed, this is basically the law of total expectation. I have derived also in the last class. How it will come, I'll not derive it. I'll just tell you the simple formula so that you shouldn't get confused, because in the last class, many were getting confused how the things are happening. So if I talk about expectation of X, it's like expectation of X given Y. So this is basically the law of total expectation. This is just the formula. Okay. Now we have applied the same formula here. How we have applied? Let's see. So I have the expectation of Y minus fx square. So the same thing we have done here. As we are given with the X, the expectation of Y minus fx square given X. Is it fine? Last time you all were having so much of problem. Now we are given with the X. The same thing. It's a law of total expectation we are applying. Fine. I've derived this. If you want to see how this formula is coming, you can see that recorded video. But many were having the doubts. So that's why I'm not going in detail how this formula came. So just writing this in the form of this. Should we proceed? Yes, class. I'm not getting any. Yes.
Yes, ma'am.
Okay. So just applying this formula. Now what we are doing is mute yourself if you are not having any doubt. So what is my main motive? I want to pick an S such that for every value of X, for every X, I should make the best prediction. I should have that fx. The function should be that it should give me a best prediction, and this loss and this gap between the predicted and as well as the actual output, it should be very minimal. Am I correct by saying this statement? So what should be my fx? Can someone tell me what is argmin of C? Till this point, I think we have discussed in the last class. Argmin also we discussed. Can someone tell me what is argmin?
The value of C which will bring out the least value in f of x.
Yes. We discussed a simple, I'll say this example, x minus 3 square. Suppose f1 is basically 4, f2 is basically f1, f3 is 0, and f4 is 1. So which value is giving me the least one? That is 3. So argument of fx is 3 basically. So the same way, argument is basically the value which will give me the output. Here the output is C, which will basically give me the minimum of the expected loss. So that I am trying to find it. What is the issue here? Anyone can suggest me, like anyone can tell me what is the issue which we can face here? Okay, I can find the value. I can find the loss. I can find the value of the C, which will give me the least of the in which I'll get the minimum of that. What is the issue which we can face? What is the problem which we can face?
For large number of input values, it will take a long time.
How, do we have Y in the first case? Actual output, true output. Do we have this? Sorry.
No, ma'am.
We don't have the true output. So what we can do? Any idea? I like what I am saying is okay. This is the true output, and then find out the C. And but we don't have the true output. What we can do?
Take the training examples from test data.
Okay. Anyone else?
Without training data, we might try to find the bias.
Exactly, both are correct. So basically, what I am trying to do is I'm trying to find out basically from the training data the y. Like what I'm trying to do is I have the pair x1, y1, x2, y2, these both x and yn. Please mute your if you're not having any doubt. So what we can do is we have the training data, we can have the expectation of that. Take all the training data point whose value is suppose x. Suppose I'm having not x1, x2. Suppose I'm having the value x. So I'll pick all the values which are having the x and I'll average them. I think so there like you are getting confused, or is it fine? What I'm trying to say, can someone elaborate? I don't want any confusion. Yes, can you elaborate? What I'm saying is, what we did is we find out, we said that, okay, we'll find out the loss function, okay? And then we did some formula and wrote it. Now, what we are saying is for loss function also, we need to know the actual y. But I don't know the y. So how can I predict it? Like in the testing data, I don't know what actual y is for that. So what I did is, suppose I have some data point, suppose x, and then which is like mapping it to some y. Like I have this x1 which is mapping to y1. So suppose I have 4-5 data points. I'll take that average and I'll say, okay, the y like x1 is equal to this data. Suppose sorry. So any doubt in this? Any doubt?
No,
So
ma'am.
you don't know the actual value of y, so you keep actual value of x, so you keep feeding x and take out the take out like 5 values of x if you feed it in and you average it out. Is that what you're saying?
Wait. I don't know the actual value of y in testing data. Okay. In training data, we have mapped it. I was having mapping x1, y1. Like I was having the mapping. Like suppose I'm drawing this 1. This is equal to 1. I'm having that, okay, this figure which I'm drawing is 1. This figure which I'm having is please, it's my humble request. Please mute yourself if you're not having any doubt. This figure which I'm having is equal to 1. So these all figures are which I'm having is equal to 1. Or the value of x1 is equal to 0.4. Value of x1 is equal to 0.4. This I am having mapping, x and y mapping in my training data. Is it correct or not? I'm having this mapping in the training data or not? Yes, who was asking the question?
Ma'am, I was.
So are you having this mapping in training data that this x is equal to this y? Am I correct? Training data has mapping. Like training data has that. Like, okay, this is input, this is output. Testing data, the same thing I'm asking. What is x1 equal to? Now, as I don't know the actual output, what I'm doing is, whatever the values I'm having, like suppose this, I'm averaging out and then I'm calculating the actual output.
Okay. So
Okay.
you're taking the testing, you're taking one testing data, putting it through the function 5 times, and then taking the average of it, and that is the value of y.
Yes, 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 yes. This was the observation. This was also not actual out. This was the observation. Like we did some observation. Look, like I put the model. I'm taking it. Like picking all those points. Now, what can be the problem here? As you said that I'm only taking the 5 points. What can be the problem here?
Training data is less, ma'am. Very small data we are considering.
There can be.
Overfit?
Yeah. Okay. Okay. So there can be a case that okay, overfitting can also be there. There can be also the case that, as you said, that yes, the points can be very less. And suppose some point is not there at all. If suppose, so I mean to say we don't have enough data points. And the second point is suppose the point is not there at all in the training. Then what? Then our average actually, if these are not enough point, that average we can't consider it as actual output, because these are only 5 in numbers, as I also took only 5. So I can't say that actually it's very like okay, this is only the actual output. I can't take those 5 numbers and say that it is the true output. Can I? No, actually. And if suppose the point is not there, then what can we do? Suppose this is a new point existing in the testing data set. So that's why we thought of relaxing the condition.
Excuse me, ma'am.
Yes, yes. Yes.
Ma'am, so in this, what we are doing is from the training data, we are trying to see the relationship between X and Y. And through that, we are trying to predict the value of Y in the testing data. Is it? Ma'am, in this, while we are trying to find the relationship, why are we only considering the values of X and not Y?
In testing data, we don't have Y actually. Testing is like we are testing. We are testing. We don't have Y. That's what our problem is. We don't have actual Y.
So in
Given.
this, when we were averaging the values of X, we were averaging the values of testing data.
Yes, yes. We are having the observations here.
Okay.
That's
So,
what I'm saying.
so till now, we have not considered the training data yet, is it?
We have considered the training data. We have the points. We have the observations I'm saying there. That our observation is this is equal to this.
Yes. I'm not getting what we are doing.
Let's not consider the training or testing. Okay, let's say that okay, I did. Let's not go like confused with the training testing. Let's go simple. I did say something. I have the observation. Okay, this is equal to this. Let's not take the actual output here. Okay, I did something. I have the output this. I did something. I have the output this. Not the actual output. These are all our observations. Let's consider this. Is it fine now?
Yes, fine.
Now I did these observations. Now let's not consider the training data, because then it will be the actual output, as you are saying. Okay, let's not consider them. Now what will be the x1? So what I'll do, I'll take the average of them. But as I have done it very less number of times, so I have less number of points. So I can't rely on those points only. Can I say that? Or I don't have actual output, like I don't have the actual observation there. Can I say that?
Yes, fine.
Is it fine now?
It's fine.
So this is basically the average is bad because we haven't tried on multiple number of inputs. We haven't tried that data point. We haven't come across that data point many times.
Okay, ma'am.
So instead of one data point, now we'll basically what we'll do, we'll condition on the neighborhood across that X. So earlier what we were saying is, we are given with X, what is the expectation of Y. Now what we are saying is, we are taking the average of Yi, and Xi is not equal to actual Xi. Basically, it's equal to the neighborhood of X. We are conditioning on the neighborhood of X, around X. What does it mean? Like suppose I want to predict the output of this function. I know this is the output, this is the output, these are the y's, and these are the x basically. So this is basically x points and these are the y points. Now what is the value of this I want to predict? So what I'm trying to say is, I'll not say that, okay, this is this point. What I'll do, I'll take the neighborhood points, because suppose it doesn't exist in that observation. So what I'm trying to do is, what is our question? What is the y of this? So let us take the average of 3 nearest neighbors, which means this one, and suppose this one. Is it fine? And whatever the average is, suppose the average lies, sorry, suppose the average lies here. So this is basically the output. Now suppose the input is this. Then also the output will lie here only, which means the y is basically constant here at this point. Am I making sense to you guys, or is it difficult to understand?
Yes, I'm getting it.
It looks more like KNN right now. Is that what
Yes,
you're
yes.
trying to do?
It's more like nearest neighbor. It's nearest neighbor only, KNN only. 3NN means KNN only. So what I'm saying is, rather than relying on one observation, one type of observation like okay, axis, we are also relying on the outputs of the nearest neighbor also, and then taking the average here. And the output will be constant if it lies between this and this point. It will be constant for them. So the other question which arises in our mind is like, what if I say that k increases? Do classifier become more stable?
Now, what is K again? Number of points.
Number of, like here I was considering 3 and 3.3 neighbors I was considering.
Okay, okay.
So classifier will be very simple.
Yes.
If k increases, classifier will be simple.
Yes. It will be more stable. Can I say it in other words? How?
Because
Suppose
the k increases means you are taking the points from the more further points you are taking and taking the average, right? So
yes.
that is the reason.
Yes. So whosoever is having the doubts, I'm seeing many doubts in the chat box. Yes, I will provide you the recorded classes. I will discuss about all these points at the end of the lecture. Don't worry. Yes, value of y becomes constant, Suma. So when I'll increase the number of neighbors, so the classifier becomes more stable in that point. So as the neighborhood points are basically getting more. Now, what can be the problem here in this case?
Outliers can affect it.
Okay, what others have to say about this? Yes, one way of thinking is yes, outlier average is there. Others? Come on.
Too much time consuming process for this one data point. Can't do it for each and every data point.
What about others? Yes. I want this session to be interactive one. Think about it.
What is the question, ma'am?
What can be the issue here?
And of course, overfitting.
When is the expectation approaches, when is actual, this will be equal to the actual output? Can I say as k by n approaches 0? What does it mean?
When k by n approaches 0, we get our expected function, the output function.
Okay, how we get, I'm getting a point what I have written. You are saying that k by n, then we get our output function. How?
N will be tends to infinity either.
Yes, they'll reach to infinity. So actually saying it that n is very large and k is very large, then only we'll say that it will approach to 0. And in actual case, then taking n so much of large, it's not that much possible. Taking the data points very large, it's not that possible. And suppose I take, suppose I say p dimensionality. What are p? Basically, these are the features. They are basically, if they are very large in KNN, I'll come to these things again, don't worry. P dimensionality becomes large. So what I'm trying to do here, everyone has got it. Like I'm taking the average, just like KNN only. I'm doing that only, rather than just relying on the single point. I'm doing that. Okay. What I'm saying is, if my k and my n, it will be very large, then only I'll get the actual output is equal to the predicted one. So, but what my p dimensionality becomes large? What do you mean by p dimensionality? First of all, yes, come on.
Is the number of features involved,
Number of
like
features.
age, price, etc., etc.
Yes,
Number of features.
yes, both are correct. Number of features like age, price, as we have discussed in the last class about the examples, like number of features become very large, then data itself become very sparse actually. So the data is far away. Sparse means they are far away from each other. They are not in forming a cluster type of things. If they are far away, then doing this KNN is not like it's not a good thing. It's not a good assumption, like idea to do this KNN thing, because obviously the average will be something somewhere lying somewhere, and because they are very sparse in nature. So that's why these issues can arise. And taking n is also a very a very large is also problematic, as in many cases, image cases, as the professor also told. It's not realistic thing, like taking n very large in nature and p very small, and p is also sparse in nature in many of the image data sets as well. Should we proceed? Any doubt here? You can ask me. So what we have done the loss function. We have done how we are basically representing it in the expectation form, and then we have done, like, suppose we are having the observation, how we'll have the like how why we are taking the neighbors one, why not we are not taking the actual point, why we came to KNN. Yes. So this part we have completed now.
Ma'am,
Yes.
can you please explain that output function again? That why? No, ma'am. The one that we just wrote.
Okay. Which one? This one.
Yes, ma'am.
So here it's nothing like what I told, like, okay, x is given, then what is y? That's what the expect, like this is the conditional probability. If x is given to us, x is equal to x, then what is y? The expectation of that. That's what we were trying to do now. The expectation of if x is given to us, and then we have to predict y, and we are taking the average. That's what we were doing.
Yes, ma'am.
So as you only asked me what you are doing, I was having the x, I was predicting what is y and taking the average of all of them.
Excuse me, ma'am. Ma'am, can you please explain again what will happen if number of Ks are increased?
Actually, yes.
Yeah,
If
yeah,
k,
yeah, yeah, please.
if k and n are increased, then it will become more stable. Our actual output will become equal to the the predicted output will become equal to the actual output. But what I am saying is it's difficult to increase so much of n, or it's difficult to increase so much of k. And the other problem is if p dimensionality becomes large. P dimensionality means features of the data points become large. Like there are features, like in the last class also we did, like suppose I have the X and what are the features I want to have buy a house, and the features are like, okay, location is one of the feature, and the other feature is like area is the feature, cost is the feature. These features become very large, then the data is sparse. Basically, data is far away from each other, and when the data becomes far away from each other, then the scaling is not that suitable here.
All right, madam.
These
Thank
were
you.
only the limitations.
Yeah.
Ma'am, here what is the n value, ma'am?
N value is the number of points, data points we are considering. Total number of data points. K is the neighborhood. Here, N is the number of total data points.
Okay.
Is it fine?
Excuse me, ma'am. I have a question.
Yes, yes.
Does whatever loss function we are taking, like it will affect the value of k? Like what loss function we are taking?
Loss function we are taking, it will affect the value of K. No, K. We are taking by ourselves now. Like, okay, I'm considering this 3 nearest neighbor or 2 nearest neighbor. How can it affect the loss function? Doesn't affect this K. Should we proceed now?
Yes, ma'am.
So the other, like, let's go to the classification part. Oh, sorry. This was the regression part. Let's go to the classification part of statistical decision theory. Though I'll not discuss, maybe, let's see. So the same way we are having the input from the real space, we are having the output as well, and a training set, data set as well. So output, as we are having the classification thing. So classification thing means, like, suppose I'm having a disease. Is this disease mild? Is this disease severe? Is this, we are not having the disease? These are the basically the classes here, which are discrete in nature. Here we have discrete in nature because we are doing classification thing. So here what we are using the general loss function, that is 0-1 loss function. Zero one loss function is like zeros in the diagonals. I'll tell you why. I'll try to explain it in a very simple way. So like, suppose I have 3 classes. If my actual output, suppose this is the actual output, this one is the predicted one. If my actual is equal to the predicted one, which means I'm having no loss here. Like, if I'm predicting that the disease is mild and actually it's mild, so which means 0 loss. If I'm actually the disease is mild and I'm predicting it as severe, then obviously 1 loss. If I'm predicting that the disease is mild and actually there is no disease, then it is 1 loss. You got the intuition behind it? Or I should explain in detail? Maybe I'll explain. Yes?
Yes, ma'am. Understood, ma'am.
Yes, ma'am, got it.
Understood, ma'am.
Okay. Then I'll proceed. So this is basically a penalty or a loss, 0-1 loss function, where zeros are on the diagonal part because they are the same. Like, whatever is the actual, that is only the predicted one. So that's why. The same way I can write EP of F. The same formula, which we have done it before. So maybe I'll not go through this. This is the same thing, the expectation, how I have written. I'll not go through this. One more thing for this. Suppose I have 3 classes. Now, suppose I don't know, suppose they are not exact. It's like I have the probabilities of them. First of all, I want to like understand, what I have written here, like these basics are clear. So what I'm writing here, I'm having 3 classes. This is conditional probability. If given X, what is the probability that the class is 1? Given X, given input, what is the probability that the class is 2? Given input, what is the probability that the class is 3? So which one is having the highest probability? What do you think? Which class is there?
The first one.
The first one. So obviously we'll go with the one which is having the highest probability. That is what we'll go with. Like, okay, 0.6 is having highest probability. So what do we think? That okay, the class is the first one. Am I correct? Or what I can do is like one. One. I'll write the simple formula here. Can you relate now? What I have written?
So maximum probability value we are considering to find out the predicted output.
Yes, exactly. Any doubts? Or I can say what I'm doing is argmax. I can say it like I have this. 1 into 0.2 plus 1 into 0.2. What is the value? 0.4 for G is equal to 1. Okay, leave, otherwise leave this. It will make me confusion to you. So basically these are giving me the higher values of the, like, okay, leave this. I'll just go with the higher probability thing. Okay, that is what they are saying. Whichever is having the higher probability, take that G part. Is it fine? Leave this one. You'll get confused. I was thinking to explain you this thing. Is it fine? Take that G value which is having the highest probability. That is what actually we'll do. Okay, that what we are predicting is, okay, the probability that X is equal to 1 is more. That is 0.6. So we'll obviously choose the text one. This is basically called Bias-optimal classifier. So which one will have the highest probability? That we'll choose, that is Bias-optimal classifier. In KNN also, we have discussed earlier only that majority one we'll choose. Like this is Y1, this is telling me Y1, this is telling me Y2, and this is telling me Y1, and this one I have to say. So these are the points. I'm considering the 4 points, 1, 2, 3, 4, and majority of them are telling me, okay, the answer is Y1. So X also I'll consider it as Y1. Fine, or I was fast? Yes,
Fine,
come on.
ma'am. Fine, ma'am.
I'll just
What
repeat it
was
once more, ma'am.
Ma'am, could you repeat it once?
This was fine. First of all, tell me. I'll repeat that again.
Yes, ma'am.
Yes, yes, please.
I have to predict this function. This function, this X, I have to predict. I know this is equal to Y1. I know this is equal to Y1. This is equal to Y2. This is equal to Y1. And this is equal to Y1. And I'm considering 5 NN, means 5 neighbors. 1, 2, 3, 4, 5. So in regression case, what we were doing the average, because that were numbers. Here we have category. Someone is saying hot, someone is saying cold, or someone is saying mild. Suppose this is y1 is equal to hot and y2 is equal to cold. So majority of them are saying me cold. So what should I do? I'll say that this is also, oh sorry, majority are saying me hot. So I'll say this is also hot. Fine now?
Yes, ma'am, it's fine. It's like
Yes.
mode.
Hmm.
Last time it was me, this is mode, right?
Yes. We can think that way also. Like in class regression, it's mean, and it's in classification, it's mode. So the linear regression part, though I'll discuss in the linear regression thing only. Now coming to bias and variance. Though we are in the week 1 lectures only, maybe I'm slow, but it's fine. Let's. Before jumping to how professor has told, I want to tell you in very simple language first of all, so that you should know what is actual bias and what is actual variance. So bias, I predicted a value and there is an actual value or target value. Actual value. So what is the gap between them is bias. Fine. Easy words. Fine. No much complex mathematics or something. Is it fine?
Fine,
Yes.
fine.
Yes. ma'am.
Fine.
Yes, ma'am.
High bias means that predicted output value is far away from the actual value.
Means the deviation is more.
Yes. Someone was speaking. I couldn't hear it.
Means the deviation is more.
Yes, yes. Deviation from the target value is more. Low bias means gap is very less. Now variance. How much scattered they are with respect to each other. That is variance. If I talk about low variance, which means they are close to each other. The points are close to each other in group, not much scattered. High variance means they are scattered. You got a layman definition, a easy definition of what is variance. You got this. What is bias? Bias, difference from actual and target. And variance, what we are observing is how close or how far these points are. No relation with their target one, just with each other. How close these points are, how far these points are. That is variance. How scattered they are.
Yes.
Let's.
So,
Now,
ma'am, when you say how scattered they are, it means how scattered the output from the actual output, right?
no, 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 no. No actual output. No actual output. Only the observations. Here, we are not talking about actual output. Here, we are talking
Predicted
about
value.
predicted values. The predicted values, whatever we have predicted from each other, how they are. Getting it? Clear?
Yes. ma'am.
Yes.
Yes, ma'am.
Ma'am, I have a doubt.
Yes, yes,
Uh,
yes.
What is the bias and variance value in case of overfitting and underfitting? ma'am?
Yes, yes, I'll come to that also.
Overfitting, it is high.
Wait, I'll come. I'll come to this. I'm going to tell you. Though I think it was an assignment also. Okay.
Yes.
I shouldn't answer it, but still, I'll tell, like, give you a hint. Okay. It's fine. So, I'll just make a chart so that you'll have the clarity. So, let's take low variance, high variance, low bias, and yes, Devi Bala means predicted by means, like, are you asking something?
मला पण द्या आदवी.
Please mute yourself if you're not having any doubt. So if I talk about, suppose this is the target lying in the inner circle. So the target is in the inner circle. Low variance, low bias means bias, like now the point is hitting this bullseye, which means hitting this target very close to the target, and they are close to each other also. So low variance and low bias. Variance means Devibala that the predicted value, how far or how close they are. Predicted y means yes, not the target one. Bias means from the target, the predicted one is how far or how close. I'm trying my best so that with like easy language, easy way, I can explain you. So now, what do you think? What will be the diagram be like? Where will be the dots?
Ma'am, the dots will be very scattered.
Very scattered, but it's low bias. So it should be close to the target,
Target,
not
yes.
far, but they should be scattered from each other.
Scattered, yes.
Now, high bias and low variance, what do you think?
High bias means it
All
should
the
be
points
away
will
from
be
Very close.
the target.
Away from the target and
Very
Close
close
to
to
each
each other.
very
Close to each other.
Can I say this?
No.
Yes.
Why?
Yes, ma'am, we can.
High variance and high bias means?
No, it's I guess
You can place them
Altogether
randomly on
scattered
the
in a
output.
circle.
Target and
Very
scattered.
scattered.
Not getting anything like one by one.
Very scattered over
Very
here.
scattered, and where?
Ma'am, you can
Away
place
from
all
the
the
target.
dots in the outer randomly.
Yes. Outer. Fine. So very far away from the target as well as not close to each other. I hope so. Is it clear the concept of variance and bias? Like I'll go to mathematical part. So
Yes.
like, is it clear?
Ma'am, please repeat low and high bias, please.
Can someone repeat? I want you should answer now. The doubts. Now I think so. I have. Yes.
Low bias and
High variance. Someone is asking.
Ma'am, in the low bias and low variance, what we have is that all the points are very close to each other because it's low variance, and because
close
the bias
target.
is also low. Yes, close to target. Because the bias is also low, it will try to be very close to the actual value.
The predicted value.
Yes. In the low bias and high variance, we will be try to close. We will try to be close to our actual value, but the points will stay scattered because the variance is high. In high bias, we'll be very far away from our target, but the points will stay close to each other because the variance is
away
high.
from the target.
And in the high variance, high bias, we will be the points will be scattered away from the target.
From the target, yes.
I hope so. It's clear to everyone. Still, anyone will have doubt, ask me in the mail or so, because now we have to. I hope so. The things are clear, or you can see again the repeated video. Still, you doubt, I can answer at the end of the lecture or mail me. Okay. Now let's proceed.
Can you explain?
Yes.
Underfitting and overfitting.
Going to explain underfitting and overfitting first, or with bias and variance. Underfitting, overfitting, though we have done in the last class, explained. Like, can someone explain what is underfitting? We have discussed in the last class.
Underfitting
Training was not good.
No, ma'am.
Training was not good, but the testing was good, we can say.
Okay, I'll come to that training testing. Simple example.
Okay.
Very simple example. I have last class also taken underfitting. Suppose in training data. I said I gave a orange. Sorry, I gave a ball. Output is a ball. And I gave the features. Whatever is spherical in nature is ball. So I have
Yes.
one feature. Whatever is spherical in nature is ball. I came to testing data. I gave the orange there. I said, yes, it's spherical in nature. It's a ball. So what does it happen? What happened here? Okay,
It is not a
I
ball.
think for today's topics, I'm going to cover, though I have to cover this also because I have, in the starting only I have asked that how you guys want to go. Is it going fine or you want me to? Okay. Continue. Testing data.
Fine.
Not many features are added.
So that's why there was an error in the testing, because if I have given that, okay, the object which is used to play, the object which is used, something like that, more features were given, then I would have tested that. No, it's not a ball.
Yeah.
Now coming to overfitting. Now, ball, suppose. Now I'm giving the features, okay, the same way, it's spherical in nature. I found a ball, something. Then I found, okay, it's used to play, okay. Then I'm giving its diameter is, or its radius is 2 centimeter. I'm giving the other feature. It's red in color. When I'm checking another ball, it's red in color. I'm trying to fit each and every feature here. Now,
Yes. Okay.
now when in testing data set, I'll see a ball which is orange in color, yellow in color. I'll say, no, it's not a ball because in the
These features and
so because there were so many features, it was trying to cover everything there. So that's over. Easy words. Is it fine? Should we
yes.
proceed?
Yes.
I'll come to your training training testing and everything. Like now, bias variance trade-off.
Ma'am,
Yes.
Prableen ma'am, once we are done with these sophisticated concepts, at the end, when we conclude this session, can we have means can I ask you something related to like development? Because I'm working on a certain project. And I'm like not able to figure out one thing which I want to ask it to you.
Okay. Sure. Sure.
It's more of a development side. It's not these mathematical concepts.
Okay. Sure.
It would be fine with you, right?
Yes. I was a mean stack developer. I have experience of that also. And now currently working with machine learning and networks part. So maybe
Okay.
I try to help you as much as I.
Yes, that's so kind of you, ma'am. Thank you so much.
Okay, let's proceed. So bias variance trade-off, prediction error, and suppose we have model complexity. So suppose here, I'll try to have something. But wait a second, I should change the color. And I'll have white one only maybe here. So what I'm saying is this is my training data. And this is my testing data. So what I'm saying is, when my model complexity is less, suppose let's focus on training data, this red part. This red part. When my model complexity is very less, okay, and my error is more, what is this case?
Error is more means
More because of model complexity is less.
high bias.
What about others, which means?
If features are less, ma'am.
Underfitting?
It is underfitting, ma'am. Underfitting it is.
Exactly. So what I'm trying to say is, I'm having less, I'll come to bias and variance, don't worry. So what I'm trying to say is, when I'm having less complex model in the training data and my prediction error is more, which means this case is basically underfitting.
Yes.
Now, when my model complexity is high and prediction error is low, what can be the case?
Overfitting.
In the training data?
Overfitting.
Excuse me, ma'am. Can you please explain this?
Wait a second. I'm getting, wait a second. Is it
Error is more, error is less. Okay, overfitting, yes.
Okay, now here testing data. Error is more, error is less, as well as prediction, like model complexity is high. Overfitting.
Overfitting, ma'am.
How overfitting? Error is less, we are saying.
How error is less?
Model is complex. How it's overfitting? How you guys are saying overfitting? Sorry, I'll again. We have a training data. Okay, I'll come to first testing one. In testing one, high error as well as high model complexity is less because of overfitting, underfitting. Is it correct? Let's
Yes,
not get confused. Correct?
Yes, ma'am.
Now error is more and model is more complex. Is it because of overfitting?
No.
No, ma'am.
No, ma'am. No.
Error is high in testing.
Testing. Now it's testing one. Yellow one is testing one. Error was high. It can happen. Model is complex and the error is high. Error is high. Model is complex. It is testing. Is it overfitting?
Yes, ma'am.
Yes, ma'am.
What about others? Having
It's
doubt.
underfitting. If it is in testing also, it's wrong. It's underfitting.
Is it underfitting? Model is complex. How can be it underfitting?
No. If it is complex, then it is overfitting.
Model is complex in testing data, and we are trying to.
Okay.
The error is more, but in training data, obviously the error will be less only in the overfitting case as well. This left hand side is underfitting. Whether training, whether testing, the error will be large in training data, obviously. And in testing data and overfitting case, like in training data, the error will be less, whereas in the testing data, the error will be more. Are the things clear?
No.
Yes, ma'am.
Yes. Anyone is having doubt, I think?
I did not get it because I was disconnected in between, so I missed what you were telling.
What is the y-axis, ma'am?
Prediction error. So what I'm saying is, again, let's come to the things. So what I'm saying is, I'm having less complex model. Okay, the model is very less complex, but my error is more. What can be the case? My error is more in training data as well as in testing data. My model is complex and error is more because of the
Underfitting.
in overfitting case, in testing data, the error will be more when the model is complex. What can be the case when model is complex and error is more? That is overfitting. But in training data set, in overfitting problems will get
Less error. Okay.
Is it clear?
Yes.
Ma'am, so do you mean to say, ma'am, sorry. Do you mean to say that overfitting occurs whenever the complexity is more? Am I right, ma'am?
Yes, when we are trying to cover all, yes, you are correct. When the model is very complex, so we have to find a trade-off. It shouldn't overfit as well. We don't want to cover all the features as well. Like I said, you okay, we shouldn't have covered the color here. We shouldn't have covered the radius feature here. We have to have a trade-off. Like how much should be the trade-off between this? These things. Can you tell me the bias and variance here?
Mm,
In overfitting, ma'am, like bias is less and then variance is more.
Exactly how?
Like
Low
what
bias and
I
high.
ma'am, what I understood is bias means error in training data, and then variance is like error in testing data. So like I understood, ma'am.
When the model becomes okay, can someone else tell why it's low bias and high variance? This side.
Because
Because error is less, ma'am. That's why we can say it is low bias. The actual output is close to predicted output. That's why
Okay,
it is low bias.
exactly, exactly. And high variance. Whenever the model becomes complex,
Yeah,
it's
yeah,
scatter.
yes.
Because it's far
That's
from
why.
its
Yes, yes.
from testing data. It is very far.
Yes, 1 minute. I was not.
The complex
Human
device. So
properties.
variance is obviously more. Am I right? No.
You remember now only before some time I was saying that p-dimensionality becomes large, data becomes sparse. When features become large, data becomes sparse. Remember?
Yes, ma'am. Yes.
Huh. The same thing. Model is becoming complex, the features become sparse, they become away from each other, and the variance become high. Got it? What is the case in underfitting?
It is more bias and
Bias,
more variance.
high bias.
Okay.
High bias and
High
High
bias
variance. High variance.
low variance.
Uh,
Because the number of features are very less, so variance will be automatically less only. Whenever the model is very simple, the variance is very low. Whenever the model becomes complex, the variance become high. The number of points become large. They become more scattered there.
Okay, okay. So
And the
you
number of
by
can
points.
more variables, then
Huh.
if we have more variables in training data,
Yes.
then there are chances that variance can be very high.
Yes, yes, yes. And when the when there are lesser variables, lesser inputs, lesser points, so there are chances that we are away from the target. We are unable to predict the actual target. So that's why it's high bias and low variance.
ma'am, can you repeat this underfitting, ma'am?
Underfitting means we have less points. We saw that when we have high.
Understood, mother. What does think about my no one we can dream now, Papa? Oh my god.
Sorry. So we saw that okay, when we have more number of points, when we have more complexity, the points may be more scattered. When we have lesser number of points, there are lesser chances of points being scattered as the points are very less. And when there are lesser number of points, we are unable to predict with close to the actual target. So which means that we are not close to the actual target, which means that model is very simple. Bias can be high, variance can be low.
हाँ,
Yes,
ठीक है,
by
ठीक है.
points, do you mean the number of like dimensions, like no, x1, x2, x3
Points, I mean to say features.
features? So that x1, x2, x3, for example, in a linear regression.
Yes, yes, yes.
Ma'am, does this apply both for testing as well as training data?
I showed you this. This applies for both high bias and low variance, and that also low bias and high variance.
Okay.
Ma'am?
Yeah.
Just a quick clarification I need. These concepts of underfitting, overfitting, are these applicable on test data or on training data? Because training data we do not have any control as such, right? Training data is something which will be available, generated by the equipment or machine or anything. But uh, but then we have some kind of algorithm, and then that algorithm will be tested based on the test data. So these concepts are applicable to test data or the training data.
This red line is training data and this yellow line is testing data. In underfitting, training data also give us high error. In underfitting, we have lesser number of features here. So in training data is also higher. Okay, this is the question for you guys only. How in training data there can be more errors? You can maybe I'll make a Slack group. I was thinking so that you guys can discuss there.
Ma'am?
Yes, yes.
One thing I wanted to ask, above the test data, I mean, where you have labeled test data, above that you have written under fitting. So
yes.
is it for the whole testing data, like you are saying that the starting point of test data, it is under fit. Are you saying that?
I'm saying yes, starting points or the points left on side are underfitting and the points right on side are overfitting.
Okay.
Should we move ahead? I hope so.
Yes, one query, is bias and variance inversely proportional?
No, we saw now that here also there is a case that low bias and low variance both are low.
Both. Okay, that's fine. One more query, ma'am. I have a doubt on rank of matrix. If you can make it anytime, not now, but yeah.
Okay, I'll share.
Thank you.
Maybe you can ask me in the mail.
Sure, ma'am.
Okay.
Thank you.
So let's proceed ahead. I was thinking to cover shrinkage methods and everything today, but let's see. Is the speed fine, or you like? I just want to ask you again and again, as I am like checking in the chat box. Also, there are some comments like we want to do today's like the other week's one. We are waiting for today's topics and all. Like, what are your views about this thing? And that speed only I'll move.
Speed is good, ma'am. But one query: this is doubt session, or like we are just discussing the topics of the week? How it is?
And it's a doubt as well as trying to discuss the topics, as everyone is having the doubts or in the maths part and in the things other things. So I'm trying to make it in more depth so that we shouldn't have problem in the sessions and all.
Got this. Got this. Thank you, ma'am.
Is it
Listener should take it with both the hands. It's very knowledgeable. We should take it, we should accept it by both hands. It is very informative and, very well explanation.
Thank you. So let's move. So y is equal to fx. What is, we are giving an input to the function and we are getting the output, and this is the noise. Some noise is there, suppose, and like we are giving the so what is there? Some function x which is predicting y, but some variable stochastic means varying noise is there, and there is a joint distribution. Going in depth, like it was mentioned in the lecture, does this have joint distribution? Why this has joint distribution? What is there? Like anyone have idea? If I'll not add noise, will the joint distribution appear? You read in lecture there is a joint distribution. What do you think about this? Come on. Okay. So suppose I have y is equal to 2, x, sorry. Suppose I have x is equal to 1, then y is equal to, I'll take y is equal to 2x. This is the function. Y is equal to 2. X is equal to 2, y is equal to 4. X is equal to 3, y is equal to 6. So these are deterministic values. There is no randomness. Suppose I add noise to them. Y is equal to 2x plus epsilon. So this epsilon value can be minus 0.5, plus 0.3, plus 0.1 for x, and y can be 1.5, 2.3, 1.9, something like that. So here, what does happen? there the joint distribution exists. How joint distribution emerges? When I'm taking 1 as x, suppose, then the y value, if suppose it's like it's like 1.5 here. Wait a second. X is suppose 2 into 1 minus 0.5. So that is 1.5 here. Or if I have 1, the value is basically 2.3 here with this. So something like that. Like something like that. The values may vary. I
How it is 1?
Yes, yes.
How it is 1 for 1 with
I'll
1.
not. Okay. I'll not go to the calculations. What I'm trying to say is like the values will vary for 1x. There can be multiple y. Am I correct?
Because the error is different.
Error could be
Noise is different. No?
So this noise basically is having the randomness there. Can I say? So that is why this joint distribution do exist here. So this is the point they were saying that with noise, the joint distribution is there. With x and y, there is a relation between them. So joint distribution do exist there. And then what does they say? That the nature of, let's take this nature of noise is equal to 0. Why this nature of expected noise is equal to 0?
So that we can get
error can be balanced out on average. Can I say this noise can be on average it's 0 on balance out on average? Can I say that? Okay, I'll not go in that detail. Let's come to simple things. Okay, y is equal to fx plus epsilon. We are taking some noise here, and it is having some joint distribution.
No, we understood. That means the mean would be 0, but the variance would be sigma square. But why would the variance be sigma square?
Is it necessary that if the expectation is 0, then variance shouldn't be something?
That's I didn't understand. So I understood. Average of all errors are 0. That's what you want to say by expectation of is 0. But then
By variance, variance is like how much noise is spread around that 0 point. Can I say? So if I'm saying small variance, this sigma square is basically small, which means all the predictions are basically close to 0.
yes. So then shouldn't
These are very close to zero.
variance also shouldn't it be 0 instead of sigma square? What's sigma?
No. Variance is not the actual. This is not the expectation. If I'm saying expectation of epsilon is 0, it doesn't mean that all the values are 0. Like suppose what I'm saying is, okay, I'll take an example. Okay, suppose 50 plus 5x. Something like that. So our prediction is like suppose actual scores are like, there are some actual thing, maybe I'll so suppose the actual scores are like 70 something. Wait a second. Something. Okay. Our students studied, and how much is the score? Let's take that example. So suppose the students studied for 4 hours and the score is 50 plus 5 into 4, that is 70 here. So it is the actual score. And what is the predicted score? It is like this. So what is the epsilon here? The noise here, 72 minus 70. What is that? 2. Here, 68 minus 70, that is minus 2. Here, what is the noise? 71 minus 70, that is minus, plus 1. Here, 69 minus 70, that is minus 1. Here, 73 minus 70, that is plus 3. So on average, what is the error here? 2 minus 2 plus 1 minus 1 plus 3. Is it going? So it's like by 5.
7 it would have become.
So
Yeah.
it's like we are saying it's close to 0 only. So suppose it's 0. I took it randomly. So suppose this is expectation is basically 0 here. That is what we are saying. But the variance, as we can say that, like they are not actually 0. We can't say they are on each other. What they are saying is that there is low variance between them, the predicted value, as you can see. And this, suppose it is 0 here. It can happen now. This expectation is 0 and the variance can be high or something like that. They can cancel out with each other. Yes, come on.
Yes.
There's variance here. You were saying that if expectation is 0, you were thinking, because you were thinking in that line that all the points are 0 here. The actual is equal to the predicted. Actual is not equal to the predicted. There is some error, but the expectation of that error is equal to 0. Do you got my point?
Yes, ma'am.
So variance,
Yes, ma'am.
So variance, how, as we have done that, how much that noise is spreading out. Now, let's go to the mathematical part. Was it clear in the class, like how variance and bias, this mathematical part came?
No, ma'am.
So this we know that x is given, then what is the expected loss? That is EPE of x naught. What is that? Should we proceed or any doubt here? If x is equal to x naught, what is the expected loss, squared loss here? This is the EPE, expected prediction error. Am I correct?
Yes, ma'am.
Now, how we jumped to this, like anyone knows, like professor told, okay, after the step, this is the variance, this is the bias. Anyone know how we came from this step to this step? Any idea? Any idea about this?
Ma'am.
What about others?
No, ma'am.
No.
No, ma'am.
Okay. Let's see. 1 minute. I'll have water and then. Yes, it's various by square, Suraj, but how we came to this step after EP? Okay. Let's see. So, what is given to us? This step. This is y minus fx square. This is actual. What is y? What is f? This is predicted one, and this is a true. Let's write this. So this is it. Expectation of y minus f bar x naught square. This is given to us. Can I substitute y is equal to fx naught plus epsilon? Can I do that? We have done this.
Yes, ma'am.
So mean square error, expectation, residual sum of the squares of mean square error, they are the same only. So let's put the value. I'll try to make it as simple as that, not like the last derivation, not making you confused. I'll just interchange, like I'll make this f here. Find the same thing, just rearrangement. Fine. Now, can I open the brackets? Square term. A square plus b square plus 2ab. Let it take this as a. Let this be b. So let us take it as fx naught plus f bar x naught whole square, a square plus epsilon square plus 2 fx naught f bar x naught. and epsilon. Fine. Till now, fine. Please mute
Yes,
your.
ma'am.
Till now, fine. Should we proceed? Nothing. Just substituted the values, rearranged, and had the square.
F x not F addition में होगा.
Ma'am, what is the last term? Last term will be another thing, right?
2ab, epsilon, epsilon. What I have done is just taken fx naught, f bar. Oh, sorry. You are correct pointing me. Fine now?
Yes, ma'am.
Wait a second. Is it fine? Wait a second. Some confusion is there. It's minus here. You should have pinpointed me. It's minus there. And it's minus. Use linearity of expectation. Anyone have an idea what is linearity of expectation?
Expectation of all the sums distinctively.
So it's like expectation of A plus B is equal to expectation of A plus expectation of B. So expectation of fx naught minus f bar x naught whole square plus 2 of expectation of fx naught, this one I'm writing, minus f bar x naught epsilon plus, sorry, the 2 I have taken it out, plus expectation of epsilons. Any doubt till now? Any doubt? Come on, tell me.
No, ma'am.
So now, what is the variance formula with respect to expectation? I have expectation of epsilon square minus epsilon expectation of, this is the variance formula. Okay. Expectation of A square minus expectation of A whole square. Variance of A. Fine. That's what I am using there. I know what is the expectation of epsilon, that is 0 here. We have already taken that term. So what is variance?
Expectation
of sigma square. Can I take here sigma square in place of this then?
Yes, ma'am.
Yes, ma'am.
So, and now let's take this term, the second term. What is it? Expectation of fx naught minus f bar x naught into epsilon. 2, let's ignore that. I'll come it out.
Ma'am,
Yes.
how did that become 0?
Which one? Okay, we have already taken the assumption that expectation of epsilon is equal to 0. So expectation of epsilon is equal to 0, then its square is also equal to 0.
Yes,
Here we have discussed.
Yes, ma'am. Got it. Thank
So,
you.
yes. So let's again use linearity of expectation. Fx naught minus f bar x naught into expectation of epsilon. What is expectation of epsilon? What is expectation of epsilon?
0.
Whole term becomes
0.
Right by 0. Now let's come to first term. So this is the first term. Am I correct? Square. It's fine. So let's take a very simple one. First take fx naught minus f bar x naught. I'll come to the square. I'll put the square and expectation. First take this one. let's write it as subtract and add expectation of f bar x naught. And just subtracting also and adding also. Fine. Just subtracting and adding. Fine.
Yes.
Ma'am,
Yes.
can I know which book you are referring?
I'm not referring any book actually. I'm just going through the lectures only. Here, this I have derived myself only, like how the things will be. Though I told you also, there is a reference there. Statistical learning book is there.
The
That
author? Can I know the name of the author?
it's written in the Swayam portal only. Maybe I'll mail you once. Like you can mail me. I'll tell you the references.
Okay, thank
It's
you.
written in the Swayam portal only. When you will open the courses now, you'll find
Yeah.
there only.
Ma'am, please make the Slack group so that we can connect
Yes,
with the.
yes. Okay, I don't
Thanks,
know
ma'am.
officially it's allowed, so we'll discuss afterwards. Okay.
Sure.
So okay. So fx naught minus. So simply what I have done is subtracted and added expectation of f bar x naught. Fine. Just rearranged them. Now taking expectation and square like wait a second. Is it fine now? So what is this? Fx naught minus f bar x naught is equal to fx naught minus expectation of f bar x naught. Same thing I'm writing. Expectation of f bar x naught minus f bar x naught. But as we know that this was expectation and the square. So let's take the expectation and the square.
Ma'am,
So
can you please scroll upwards once?
Yes. Nothing I have written. Same thing I have written. Just I have written the right hand side. This one. What we started from here now. That fx naught minus this is same thing. Upward. Same. Okay. Same thing. Just now because it was expectation and we want the square. Now I'm taking the expectation and I'm taking the square both sides. I'll come again once. I'll come once again with this derivation. Don't worry. So again, fx naught minus expectation of f bar x naught square plus expectation of f bar x naught minus f bar x. So we got this value. This is equal to this one. I'll come again. Don't worry. So this is equal to this one, and the last value, the middle value was equal to 0, and this where we started. So here we started. We took the three values. One was equal to 0, as we have seen. This one was equal to 0. The last one was equal to sigma square. We saw, and the first one we derived this. Is it clear? Now, can I write this same value? The expectation of fx naught minus expectation of f bar x naught square plus expectation of f bar x naught. One was equal to 0, the middle value we have done, and the last value was sigma. This was only the professor has told. Am I correct? Should we again once go to the derivation, or is it clear? Like, I don't want that you should just cram the steps. I want that how this is coming. That's what I have to tell you. Like how we jump from this step to this step. Is it clear, or I should move again?
This is all prerequisite for the concepts for machine learning, right?
No. It's like you should know about more about probability or expectations and all, like probabilities or linear algebra and all. But it's fine if you don't know. You can learn side by side. Like these are the formulas which I use, like linearity of expectation. This was just a derivation which he has not told. And many of you might, I was also getting difficulty, okay, by deriving. It's fine, totally fine, like how we went from this step to this step. It's totally fine if you don't come to know at that point, okay, how.
What I'm trying to ask is in which concept we are going to use all this in machine learning concept, like in dynamic learning or in something like in reinforcement learning, we are going to use this expectation law and all, right?
Machine learning, what is happening behind this linear regression, what is happening behind this variance and bias. When we are taking these data points, we have to take care, like when we are taking the features, we have to take care how much is variance between them, how much is bias there. So that's what we are saying, what we are deriving here. Maybe when we'll do hands-on practice, then you'll come to know how the things are going. Don't worry.
That is what, ma'am. It is just a prerequisite, right, for the machine learning concepts.
This is a part of machine learning, I'll say.
Okay.
Okay. Okay, can someone tell me, is it clear or not?
Can you explain the last that bias plus sigma square, that one?
Okay. I'll and what about others? Should I explain from starting once again?
Yes.
Once. Yes, ma'am. It would be better.
So I was in this step, how we jump to simply this equation, how we came to this equation, that I'm trying to make you understand. Y is equal to fx naught plus epsilon. We have done. Just substituted that fx naught plus epsilon minus f bar x naught. Fine. Just substituted that. Just rearranged that fx naught minus f bar x naught plus epsilon whole square. Fine. Fine.
Yes.
Yes, ma'am.
A plus b square. A square plus b square plus 2ab. Fine.
Yes, ma'am.
Yes, ma'am.
Linearity of expectation. What is that? When we are writing expectation of A plus B, then we can write it as expectation of A plus expectation of B. The same way, I took the first term. Not the first. Okay. Sorry. I took the whole term and I have written expectation of this plus expectation of this plus expectation of this. We have three terms now. Fine. Expectation of this plus expectation of this.
Yes, ma'am.
I took this term to epsilon 1. Or, okay, first I have taken this. Epsilon, we know the variance formula. What is the variance formula? The expectation of epsilon square minus expectation of epsilon whole square, which means epsilon variance of A is equal to expectation of A square minus expectation of A whole square. You should remember this. Okay, when I have to write the variance in terms of expectation, this is the formula. So I have written this. Fine. Fine.
Yes, ma'am.
So I've written expectation of epsilon square minus expectation of epsilon whole square. I know what is the expectation of epsilon, that is 0. Wait a second, I'll come to a development question. Wait a second. So expectation of epsilon is equal to 0. So its square is also equal to 0. So I have expectation of epsilon square. Now, which is equal to the variance. I can write it as sigma square to the variance, what we usually write. So this third term is equal to variance. Fine?
Yes, ma'am.
Then I came to second term. What is second term? Expectation of 2 into expectation of fx naught minus f bar x naught into epsilon. Again, what I did, this is not linearity of expectation. This is just I'm opening the brackets, expectation of this into expectation of epsilon here. As these are independent terms, epsilon and this term. I know that expectation of epsilon is equal to 0. If it is equal to 0, if I multiply this is equal to 0. Anything multiplied by 0 is 0. So the second term becomes fine.
Yes, ma'am.
Now coming to first term, which is equal to expectation of fx naught minus f bar x naught whole square. This is the first term. I just took fx naught minus f bar x naught. What I did, I subtracted expectation of f bar x naught and I added expectation of f bar x naught. Fine, I can do anything, like if I'm writing 2 plus 3 minus 2 plus 2, I can do. Doesn't make a difference.
No, ma'am.
Should I
No,
proceed?
ma'am.
Yes.
Yes.
Yes, ma'am.
So I took a bracket fx naught minus expectation of f bar x naught and expectation of f bar x naught minus f bar x naught. So what is equal to? So I'm just writing the full this thing fx naught minus the same thing I have written, same thing. Fx naught minus this plus this. Now, as I know that what I have to do at the end, I have to take the expectation. So what I did is I took the expectation on the both side and square it up. So that is what I have done. I didn't written same thing. So I have done the expectation and squaring it up. And the third term was 0. So that's why a sigma square. That's why I've added sigma square. Fine. Fine.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am. It's
Any
fine.
doubt? Now you
Yes.
can
No.
see how we jump to this step.
Yes.
Yes, clear.
Now, what is this term? Anyone have any idea? This is the sorry. This is the predicted value, and this is the
Predicted value.
how far is the actual value from the predicted value? What is this?
Bias.
Bias. Exactly. Bias square. What is this?
Variance.
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 Square is there, I think. I've missed it. Maybe. Is it square or is
Variance. No, it's not a
No,
square.
it's not square.
With the
Not
square.
square.
So what is this? Variance. How it's variance? Anyone?
It is telling that how far is the output from the actual value.
So how far is the output from the actual value? Oh, no. That is bias. What is variance? These all, I told you.
How close or how
Scattering of
Scattered.
How scattered.
Close is
how much scattered
scattering.
it is.
So how scattered it is, that is basically variance. How can we say that this is as variance only?
If it is scattered from from the target and from each other, then we can say it's
It's not
variance.
target. There is no target in the variance. Variance is how scattered they are from expected value from, or how far from the observation from the mean, basically. So how scattered they are from each other. That is basically the variance. Fine. And this is the square. That is
Ma'am,
basically.
here we are checking the average.
Yes.
The output and the output.
What?
Variance.
Can you repeat the question?
Ma'am, double expectations we are using here. Huh?
Yes.
Expectation of a predicted output to the expected output.
This is expectation of the predicted output, and this is overall expectation. How far is the predicted output from the expectation on average? Like, which means how far from, wait a second. I have to calculate like a point is how far from each other. They are how far from each other. Or I have to calculate the point is how far from the mean. That is the same thing. From mean to point. So that is why they are saying it as average. On average, how far is that point from the expected points? Is it fine?
Yeah, fine, ma'am.
What about others?
Yes,
ma'am.
Yes, ma'am, it's fine.
Yes, ma'am.
So I hope so. This bias variance is fine now.
Yes.
Ma'am, variance should be square, right? In your
that's what I was saying. It's square only. Maybe some
square should be there, right?
That's what I was saying. That something is wrong. Somewhere I have missed something. Okay. I think so. I have missed here only. It's square only. Expectation of expectation. When I'm taking square and expectation, maybe I have missed here.
Ma'am, what was this?
In the second line, you missed it, ma'am. Only the internal part we have expanded.
This is here I have missed it. I have taken the expectation and I have to take the square as well.
Ma'am, what was the sigma?
Sigma is the noise. The independent variance basically means the noise here.
Noise.
Variance noise here. So let's proceed. Let's take, if I talk about KNN part.
KNN is
K nearest neighbor.
K nearest neighbor, yes.
What is the variance of it? I think it's told in class.
Minimum, max, minimum.
Can someone tell me how? It's told like variance is equal to K sigma square K over K. How?
Because we are calculating for k number of data points.
Number of features are more there.
How this variance is this? Let's see. Let's have that.
Because noise is
what is the prediction I'll come to that. Don't worry. Now, what is the prediction we take in KNN? We take the mean of K numbers. That is what we do.
Yes,
So,
ma'am.
what we do, the prediction, y bar is equal to 1 by K, y1 plus y2 till yk. That is what we do. I can say it 1 by K, sigma I, yi. Please mute yourself if you're having any doubt. Clear?
Ma'am, you have some option to mute all. Okay.
Actually, if I'll mute all, someone will have doubt, and I don't know. That's why I'm not muting all. Though they can unmute again. Okay. Let's proceed. Is it clear? Clear?
Yes, ma'am. Yes.
So now taking the variance. So one more thing. Formula. What is the variance of AX simply? Anyone have an idea like how we write the variance of AX?
A square variance.
A square variance of x.
So how we'll write the above one?
R square variance.
1 by K square. Sorry, it's K, not R. Sorry for my writing. Variance of sigma I yi. Can I write? It's fine.
Yes, ma'am.
Now, variance of sigma I yi. If x and y are independent, like variance of x plus y, so I can write it as variance of x plus variance of y if they are independent, like linearity of expectation as well. So I can write it as sigma I. Obviously, it is independent, like yi. Any doubt in this, what I have written? Anyone can explain if you're not having any doubt, or if you have any doubt, ask. Come on.
No, ma'am. It's
not
okay. Yeah, understand.
get this step.
Huh? Yes.
I did not get this step, the last step.
Can someone tell? Yes, come on.
K times sigma square upon K square.
If I'll do this sigma square K times, what is this? K into sigma square? Can I write?
Yes, ma'am.
Yes, ma'am.
That is what, if I'll do 2, I'll do this. Can I write 2 into 3? The same way we have written. Fine now?
Yes, ma'am.
Fine. Any step you are missing? Is it fine? So now substituting it back, 1 by K square into K sigma square. Is it sigma square by K? That is what the variance is. Fine. Fine.
Yes, ma'am. Yes, ma'am.
Go back to the last step. Just you wrote
Yes, yes,
there.
yes.
Yeah.
Any doubt?
No, ma'am.
Okay, it's okay, ma'am. Yeah.
Now, bias thing. Let's see the bias. I think professor has written reverse in one of the like above thing and then again reverse it, though it's like this only. Maybe he has written it, but maybe we can reverse it. But when we derive it, it was like this. Afterwards, he was also using the same thing. Okay. What is f bar x square? X naught in KNN? Am I correct? What is the predicted value taking the average of the nearest one? Correct, na? K nearest one. Correct? Should we proceed?
Yes, ma'am.
Yeah, yes, ma'am.
Yes, ma'am.
Taking the expectation.
Oh, man.
It's constant only. That's why I'm bringing the expectation outside. Sorry, constant outside. I can write fx I plus epsilon here. Ffx basically, if I'll say epsilon, expectation of epsilon is equal to 0. And we have seen that f of xi, the observed value, it's a fixed value only. So I can directly write it as f of xi. So here I can replace this f bar x naught by this value. Is it fine? Any doubt?
No,
If
ma'am.
No, ma'am, it's fine.
Pratibha, I'll come to your question. Don't forget. Now just substituting these values again. Just in the variance part, this bias part. So f of x naught was the actual target one, and then the expectation of this one square. So this is basically variance, bias, how we have written in other terms. Is it fine how this came, basically the formula came? Come on, or confused? How much the expected value, what we are doing is far away from the target one, the bias one, how much variance, how it's behaving, and sigma square. So just we have written the this equation in terms of variance and bias here. The same equation we have written here. Do you got the concept of variance and bias today? Like from the simpler concepts, overfitting concepts, this low variance, high bias, and everything. I thought to cover the.
Yes.
Yes, ma'am.
Concept is clear, ma'am. Derivations are a little tough.
Maybe you can see the video once again. I tried. Actually, these derivations are not there. But if obviously, if you'll go from this step to the next step, you should know like how to group. Oh, it's like you shouldn't cram. I don't want how you are going. You should at least know these are not that tough. Once go go through it. If you will again have doubt, mail me there.
This
I'm
will be in your YouTube channel, right? Then we can go through it one by one.
yes. I'm writing my YouTube channel here again.
Ma'am, can you share the notes of PDF link?
Yes.
I've shared the last one also in the comments. Someone has commented, so I have shared. Have you seen it?
No.
You can see that someone commented about the notes, so I have shared that there also. And this is the YouTube channel. This is my mail ID. I have responded to the people who have mailed me.
Ma'am, is it the right time? Can I go ahead with my question?
Yes.
Ma'am, before that, I just want to have one question.
Yes.
Regarding this assignment, whatever the assignment we see, like 12, like that is the final assignment for this every week, right? Do you
Yes.
have any other than MCQ? Any assignment other than MCQ? No, right?
No. Those assignments which you are looking at this WAM portal, that are the final assignments which you have to submit.
Sorry?
Those assignments which you are looking at the SWAM portal, the portal which you are enrolled, that are the final assignments there. Every week you are getting the assignments now that you are submitting.
Yes.
Actually,
Yes.
there is a marks for 20, 25 marks for assignment, and based of eight based of 12 will be taken, but it's not total. That each assignment is not up to 25 marks. So that's the reason I had the question.
I'm not getting it. What you are.
Each assignment, sorry, the assignment marks will be 25 marks, right?
Okay. They'll average out. And
They'll average. Okay, fine.
Okay. Okay, if the comments are not there, I'll enable the comments and all. And YouTube link, is it not visible to you all? If you're searching it, I don't think so. It's not visible. Maybe I'll say. Is it visible or not?
Could you please tell us again the link, YouTube link?
It's visible, ma'am.
It is visible only, ma'am.
Can someone send in the chat? Okay, and notes, I'll enable the comments maybe. Or wait a second, I'll.
Could you please tell the name?
I've written the name in the comments. You can check. Someone has sent the link. I've written the name as well. You can see. If you still have any doubt, you can mail me. The mail is also there. Wait a second. I'll share you the notes as well. Don't worry. One. So I want to have the feedback also. Meanwhile, how was the lecture today? And what are the changes you want or something like that? Please see the, please you can copy paste the notes link. I have shared the drive link with you. You can see there.
Okay.
Yes. Now can you about the feedback? Yes. As we are moving very slow, I know should we increase the speed? Should we how the things should be ahead? Can someone suggest and regarding today's video lecture, is it clear? Or there are some doubts? There is some.
Ma'am, there's no need to speed up or slow down because as you see that the conceptual clarity is equally important. So मेरे हिसाब से this is the optimal speed that we are heading in.
Okay. Yeah. And I think the other TA has covered. Is it so, or she's also lagging behind?
Ma'am, she's going with the week only.
Okay. So they are also working like this only, mathematics and all, writing and all.
No, ma'am.
Okay. Okay. Yes, someone was having a doubt, yes, about development and other doubts also.
Yeah, ma'am. It's me.
Yes.
The question is basically I'm trying to build this project. It's an AI project wherein I'm building an Edge AI project. Okay, where Edge AI project as in where the request is handled, where the AI all the processing that happens on device. It doesn't has an API that just sends it to the server
Okay,
and
okay, okay, okay.
we are not using any API or
Backend you are not
making a
using.
call to OpenAI or something. So, जो भी करना है, we need to do on the device itself. So I'm building this project, an Android app wherein I'm building an app where the students, it's for the students. Okay, what happens is suppose when a student attends a lecture. When a student attends a lecture, they can just click on the start lecture button, and the lecture would start recording. Okay, whatever the lecturer has spoken would get recorded and would be saved in an audio file. And after that, I would need an model that just transcribes everything that's what's spoken into English, and all that textual content would be sent to an on-device large language model, which would be embedded into the app itself, no, which will take the entire text, the transcribed text, and would just derive the summary of that of like
Okay.
10 sentences or 20
Okay.
sentences. And that's why
Okay.
and this is the project that I'm trying to build. N- and I'm seriously struggling with what should be the architecture and which model should I use and all that. Would you guide me with this?
Okay, maybe you can mail me about this thing. I'll think about it, like about these things. You can mail me. I'll reply on the mail only. Is it fine for you? I'll think about this thing. Like
I don't have your email address, ma'am.
I have written in the chat earlier. Also, I'll again try.
Somebody please resend it. It's getting hard for me to like.
Yes, yes, I have sent it. Don't worry. I'll like mail me. I'll reply you back there.
Okay, ma'am.
What about others? Are you having any doubt?
We'll go through your lecture notes once so that we can pick up
Yes, yes.
line by line. But thank you. Thanks a lot, ma'am.
Ma'am, what do you think about the idea, ma'am? Is it
The idea is good. Actually, it's good. Like you are summarizing and all. That's a good idea. Like I'll think like how this architecture and models should be proceeded.
okay?
The idea is actually good.
Thank you, ma'am.
Discuss on the mail. Yes.
Thank you.
Thank you so much.
Yeah.
Thank you, ma'am.
Thank you. Thank you.
Thank you.